Exercise 8.1. The question is to design a positive pressure dilute phase pneumatic transport system to carry 500 kg per hour of powder with particle density of 1800 kg per meter cube and mean particle size of 150 micrometer across a horizontal distance of 100 meter and vertical distance of 20 meter. Assume the pipe is smooth and there are four 90-degree bend and the allowable pressure for the system is 0.7 bar. So the first one is we need to assume the pipe diameter. So for this solution, we assume the pipe diameter is 50 millimeter respect to the inside diameter of the pipe, and then determine the gas velocity, which by using the risk correlation. So the risk correlation is shown here, uh, and we need to rearrange the equation so we can find the saltation velocity. And then the obtained saltation velocity is 9.21 meter over second. And to calculate the superficial gas velocity, usually we need to time 1.5, which it is considered the safety margin. Hence, the superficial gas velocity is 1.5 times by the saltation velocity, and the obtained value for the superficial gas velocity is 30.82 meter over second. Next, we proceed to the pressure loss calculation. First, we proceed to the horizontal section. For this section, we use Hinkle correlation. The Hinkle correlation usually have six terms, which is the first and second term is respect to the acceleration of gas and particle, and the third term and fourth term is respect to the pipe friction, and the fifth and sixth term is respect to the static head. But for the horizontal section, we can neglect the term number 5 and number 6 since the theta of the static head is equal to 0 for horizontal pipe. So this is term number 1, term number 2, term number 3, and term number 4. And then by using the I'm sorry. So first we need to find the particle velocity for the horizontal sections. So the equation is as stated here. And from continuity equation, we can find the velocity of the fluid, which is our gas for the horizontal section. So for both velocity, the particle velocity is 11.15 meter over second. Meanwhile, the fluid velocity is 13.87 meter over second. Then we need to find the friction factor. So to find the friction factor, we need to use CD. So the CD is obtained from the correlation from equation 8.19. By using the fluid velocity and the particle velocity obtained earlier. So we need first to find the Reynolds number for the particle, which is 26.6. Then follow these correlations. We choose the suitable equations and correlations to be used. So by using this equation, we can find the CD value, which is 2.58. Then we can find the friction factor for the particle using this equation and get the value of 0.01279. So as for the friction factor for the gas, we need use the Blasius correlations for smooth pipes, which given in the equation. So we need to find the Reynolds numbers of the gas Then just put in the value in the equations and you can get the value of the friction factor for the gas, which is 0.054. After that, when the needed value is obtained, then we can proceed to calculate the pressure drop for each term. So for the horizontal section, we calculate the pressure drop for the first term, second term, third term, and the fourth term, and we total up for the horizontal section. So next, we proceed to the vertical section. For vertical section, we also use the intercorrelation, but this time we neglect the term number one and number two, which is respect to the acceleration, because the initial acceleration of solid and gas was assumed to take place in the horizontal section, so we can neglect it. And then the term number four, which is this, is modified by using the Kono and Saito correlation, which is equation 8.16, and the theta of the term number 5 and number 6 uh, is 1, since the degree is used is 90 degree. Then, by assuming the particle behave as individuals, uh, the particle velocity for the vertical section can be correlated using these equations. And for the continuity dissipation, we can find the value of voidage for the vertical section by combining this equation and these equations. So this is the mathematical solutions. Then we can get this equation for the solving of the equation to obtain the value of voidage for vertical section. So uh, in this, so for find the this voidage value, we need the terminal velocity value. So how we can get the terminal velocity value? Can use these two equation. Which is first we find the CDRE square T, which is respect to the terminal velocity. Then we obtain the value of 281.45, and from this figure, uh, the value 200 something is here. Then I drag the line along the graph until it intersects with the curve of CDRE square. Then I go to the bottom of the graph to take the reading, and from this figure the RET reading is 6.9. So the 6.9 is used in these equations to find the terminal velocity, which is 0.705. Hence, by using the obtained terminal velocity value, we can proceed to calculate the voyage for vertical section by inserting the value of the terminal velocity in these quadratic equations that we obtained earlier, and then we can get the value of the voyage, which is 0.9970. So same as before, we proceed to calculate the pressure drop for the vertical section, which is for the term number 3, number 4, number 5, and number 6, which is then total up that we can get the value is 3413.88 Pascal. So this is the summary for the total pressure drop for horizontal and vertical section. Then we proceed to calculate the pressure drop for the bend, sorry. So usually in industrial practice, the pressure drop for bend is approximately equivalent to pressure drop for 7.5 meter of vertical section pressure drop. Hence, first we need to calculate the pressure drop of the pipe for each meter. So we divided the pressure drop for vertical section with the length of the vertical section, and then we can get the value of the pressure drop per meter for vertical pipe. Then for the total pressure drop for the 90-degree bend, we times the number of bends, which is we have 4 bends, and we times the pressure drop, and then we time the 7.5, which mentioned earlier that the pressure drop for bend is usually equivalent to the pressure drop for 7.5 of the vertical part. So the obtained value is 5120.82 Pascal. So then we have calculate the pressure drop for horizontal section, vertical section, and the loss pressure across the band. So then we just total up the number, and we can get the value of 54,061 Pascal, or when convert into bar, we can get 0.5 bar. So the conclusion for this calculation is uh, the allowable pressure loss for the system is 0.7. Allowable pressure is 0.7, and then the calculate we get 0.54. This is indicates that we are follow the requirement, which are mean it not exceed the allowable pressure, mean it is safe for the pipe to work for the system. So what happen if the calculated, for example, if the calculated value here exceeding the value of the allowable pressure, which is 0.7, then we need to uh, start again the calculation by using the different diameter of the pipe, and then we compare the obtained total pressure drop for the system, which is it is exceeding or not of the value of the allowable pressure drop. So that's all for the solution for the equations. And thank you.
From exercise 8.2, the given mass flow for particles which is 2000 kilogram per hour. The diameter is 0.05 meter. Particle density is 2500 kg per meter square, and the fluid density is 1.2 kg per meter square. The particle size given is 150 micrometer. To test whether the system will operate, we will first check the air volume flow rate at the satisfaction. So, the first step we need to know that the superficial gas flow rate must exceed the choking velocity. So, based on the equation 8.1 and 8.2, we need to find the solid flux, which is G equals to mass flow per area, and also we estimate the particle terminal velocity UT equals to 1.77. Then we will substitute equation 8.1 in equation 8.2. From here, we'll From here, we're going to rearrange the equation to get the voidage of choking. So the voidage of choking is equals to 0.9705. Once we get the voidage of choking, we will then substitute back into the equation of 8.1. Therefore, we'll get the velocity of choking, which is 5.446 meter per second. But the answer that we'll get is a predict of choking velocity. As to get the superficial gas velocity, we need to times the choking velocity with 1.56, which is the safety margin. So therefore, the answer of our superficial gas velocity is 8.44 meter per square. The next step is to calculate the lift line pressure loss at this gas flow rate and compare it with the available blower pressure at this flow rate. The pressure loss in the vertical section of the transport line is given in equation 8.15, but we need to substitute equation 8.16 in the equation 8.15 to get the pressure loss. To use equation above, we need to find the voltage of suspension in vertical. So to find it, we will use the equation of particle mass flux and calculate it using simultaneous equation, and at the end we will get the voltage of suspension, which is 0.9835. With this, we can continue to calculate the actual gas velocity and also the actual solid velocity, which will get the actual solid velocity is 6.86 meter per square.
Thank you, Huda. Assalamualaikum and greeting to Doctor. I am Narsha Balkis and I will proceed 8.2 exercise with the pressure loss of components in the vertical pipe. First thing first, let us calculate the gas acceleration by using this equation as shown in the slide. By substituting all the information given into the equation, we can now obtain the gas acceleration which is 43.9 Pascal. Next, I will proceed with the second term by substituting the information of density particle into the equation and obtain 970.5 Pascal for solid acceleration. For the third terms, as shown on the slide, we will be using a Reynolds equation to obtain the Blasius correlation for smooth pipe, which is denoted as FG. Prior to obtaining to the FG, we need to calculate the Reynolds number first by substituting the diameter times with the density of fluid times with the supercritical velocity divided by mu. After obtaining the Reynolds number, substitute the value into the FG, which is 0.079 times with the Reynolds number the power of negative 0.25. Hence, we obtain 0.0061 for the Blasius correlation for smooth pipe. Then we can proceed for the third term, which is to obtain the gas friction. Hence, the gas friction value is 1059.1 Pascal. We can move to the next term, which is the term 4, by substituting all the information into the equation as shown in the current slide. 0.057 times with G LV times with the G over D. After substituting all the information, we can now obtain the solid friction which is equivalent to 11,293.6 Pascal. The next term, which is the term 5. The term 5 is to obtain the solid gravitational head. And we now obtain the solid gravitational head value, which is 20,226 Pascal. The last term, which is the term 6. Term 6 is gas gravitational head, and we obtain the gas gravitational head at 579 Pascal. Hence, the total pressure loss across the vertical section, or denoted as delta PV, is equal to 33,160 Pascal. This can be obtained from the equation as shown in this slide. And I would like to mention that the available blower pressure at this maximum flow rate is 0.3 bar, so the lift line will not operate as required. By reducing the gas velocity safety margin will not have, since this will cause the line pressure loss to increase. So that's all from me. Thank you.